Hello everyone. Welcome to our online course on this computer network. So in the last few lectures, we have talked in details about the different routing protocol that we have. We have also talked about the CIDR routing mechanism, how the routers find out the destination IP address from a packet and then make a match with its routing table to forward the data to the next hop interface, and how these routings are being performed. So we have looked into all those details. Now in today's lecture, we are specifically going to learn about the router architecture and what are the different components inside a router. So let us start from that point. Okay. So if you look into the life of a router, it is a kind of a repetitive mechanism. So the router, basically, whenever it is getting a new packet, the task of the router is to find out the path for the destination IP address, which is there in this packet. And after finding out the path, build up the CIDR routing table, and then forward the packets by following that CIDR routing table. And then again, whenever there is a routing change or there is a path change, again build up that CIDR routing table and again do the forwarding operation. So these are basically the two different tasks that the router performs. So one is to finding out the path for a packet towards the end destination, depending on the different routing protocol that we have studied, like the distance vector routing protocol or the link state routing protocol. And once you have that routing table based on the routing protocol, then forward the packet depending on the routing table that the router has constructed. Now, that way, every router has two basic operations. One operation is constructing the routing table, and the second operation is that do a routing match and forward the packet to a dedicated interface through which the packet can be forwarded to the next. Now, typically in a router, we say that building up the routing table is the task of the control plane of the router. That means it basically try to design a control structure over the network because it needs to understand the network topology, finding out which are the neighboring hops, then find out that which should be the next hop if I want to forward a packet to a destination IP address. So these are the kind of control task of the router. So the task where the router is actually performing to build up the routing table, that particular thing we call as the control plane of the router. And then for every incoming packet, the routing decision which are being taken up, that we call as the data plane of the router. That means the data plane of the router is basically taking the packet, finding out what is the destination IP address, making a match with the routing table, and finding out that what is the outgoing interface for that packet, and then forward the packet to that outgoing interface. So that way we separate out the control plane and the data plane of a router. We'll look into the details about this control plane and data plane in a router. Now, if you look into the evaluation of the router architecture, the first generation router, which were there until 1980s, they are the standard computer with multiple interfaces connected. So you can get packet through one interface and then forward it to other interface. So the routers were just like a standard computer. Now, the second generation of the router, which came in 1990s, they delegate to specific routing interfaces. That means you have multiple downlink interface as well as a set of uplink interface through which the router will get connected. And then there can be multiple devices which can be interconnected to that router. The third generation of the router, which came in late 1990s, they follow a kind of distributed architecture. The distributed architecture in the sense like you have multiple routers, and the router control plane, as we have learned in the distance vector routing protocol and the link state routing protocol, they are distributed in nature. So that kind of distributed architecture came into practice. Now the fourth generation of the router, which came in early 2000s, and currently we are actually using that kind of router. That is the distributed over multiple racks. So You have different rack and then rack mounted routers in every individual rack. I will going to show some picture of that, how that rack mounted router look like. And then today we are gradually moving towards the 5th generation of the routing technology, which is called the software defined routing. So we'll talk a bit about this concept of software defined routing. Now, if you look into the basic architectural component of a router, so one side of the router is the interface card. So this is basically the kind of distributed router architecture that we are talking about. So you have multiple interface card, and every interface card will have their own microprocessor. So the task of this interface card is to take an incoming packet and then process the packet to find out the header field of that packet, and then do the match and all those stuff that will be done in that upper part, that is the processor part. And then that is for the incoming packets. Now for the outgoing packets, the interface card will maintain outgoing queue. Now whenever a packet is pushed to that outgoing queue, the interface card will again look into that packet and then use the lower layer of the internet protocol stack to forward that packet to the communication media, either it is wired or it is wireless. Now this routing processor, that is a kind of dedicated processor which is basically built up to do the routing task. The routing processor has a memory as well as a CPU. The CPU is used for actually many purposes. One is to do that route lookup, and another thing is to run the routing protocol in the router. Say whether you are going to run a distributor distance vector routing, or whether you are going to run a link state routing, the corresponding routing protocol is executed on top of this CPU, or better to say the top of this routing processor. So through this routing processor, we are actually doing all the processing activities of the router, and then the interface card, which has that incoming queue or the outgoing queue, where you are receiving the packets and then doing the packet level processing, doing the routing table match, forwarding it to another outgoing interface, and through that outgoing interface, you are forwarding the packet to the next one. So typically, it might look like something like this. Say this is the incoming interface through which the router has received the packet. Then through this interconnection network which is within the router, through which this multiple interface cards are interconnected. Now, with this interconnection network, you talk with the routing processor, and that routing processor has the routing table inbuilt. So you make a construction with that routing table, find a match from that routing table, and say this routing table says that, well, you need to forward the packet to this 4th interface card. That means say this CTH4. So forward the packet to the outgoing queue of this interface card, and through this interface card, the packet will be forwarded to the next one. So this way typically the entire architecture works. Now, as I was mentioning, that the processor is responsible primarily for the control function. They are the dedicated processor which we call as the route processor. So this route processor are particularly used for constructing the routing table based on the routing algorithm which you have configured for your network, whether it is a distance vector routing protocol like the OSPF, or a link state routing protocol like RIP. So whatever routing protocol you have constructed, the processor actually runs that routing algorithm and develop that routing table. And this forwarding is done at the interface card. Now, typically you can think of that whenever you are doing that forwarding, this interface card need to be very fast, because per second, you just think of a router which has an outgoing interface of having a 10 Gbps link. That means per second, at most you can get the packet at a rate of 10 Gbps. Now, if you think about every packet size as 1 KB, then you can estimate that the number of packets that you are getting per second. Now, that many number of packets need to be processed, need to make a match with the routing table, and need to be forwarded at the outgoing interface of the router. So that is why this route match needs to be very fast, extremely fast. For this purpose, we use a kind of specialized hardware. We'll talk about that hardware later on. It is called a ternary content addressable memory, or TCAM. Typically, this is actually one of the interesting difference between a router and a switch. So typically a switch do not make this kind of routing table match. The algorithm which is being used in a switch, that is a very simplified algorithm through which it just forward the packet. So that is why the switches are much more lightweight and much more cheaper compared to the router. So one of the major reasons because of which the router becomes very much expensive, because of this specialized hardware like the TCAM which is being used inside the router. Because of this TCAM, the router becomes very expensive compared to the normal layer 2 switches. Now, as I was mentioning that broadly this router has two different planes, the control plane of the router and the data plane of the router. Now the control plane of the router, it is responsible for the routing table construction, and the data plane of the router, it does the forward. So this is the internal structure as I was mentioning. Like you have the interface processor, which actually maintains the incoming queue and the outgoing queue, interface queue. Then it is connected to an interconnection fabric. It is connected to a packet processor. So this packet processor is basically a microcontroller which is mounted with each interface processor, or sometimes it also can be mounted with a route processor depending on the router architecture that you are building up. So this packet processor actually contains the forwarding engine, and then you have the route processor which contains the routing engine. That the task of the routing engine is to build up the routing table. So this route processor and the routing engine, that is the part of the control plane, and the remaining part where through the interface processor you are getting the packets, doing the forwarding through the packet processor, which is the microcontroller. That is the part of the data plane of the router. Now, as I was mentioning that how a router looks like, so if you look into this diagram, the right side diagram, so that is basically a router look like. So a typical distributed router look like. So you have multiple different interconnecting interfaces. So here you can see there are 4 different interfaces, this 1, 2, 3, and 4. So there are 4 different interfaces, and these interfaces are connected through that interconnection network to a route processor. So on this board, there would be the route processor. So that is a kind of a single routing board. Now, in typical in a slotted chassis, what we do that I have multiple interface cards with me, and there is the route processor. They are connected over a chassis, and they build up a kind of rack architecture where in each chassis you have one blade where you have these different interface cards, and then in one blade you can have the route processor. So these interface cards are inserted in slots, and the route processor is also inserted in slots. So this kind of combined architecture actually simplifies and repairs the upgrade of different components inside the router. Now let us look into the different functional components of a router. So as I was mentioning that there are 2 different planes in a router, the control plane and the data plane. So the control plane of the router is responsible for running the routing functionalities. So it will update the table and build up that routing table. Then the data plane, or sometimes we call as the data path of a router. The task of the data path of the router is to do the per packet processing. So whenever there is an incoming packet to this router, it will do a route lookup, find out what is going to be the destination interface for that router, and it will output that packet to the corresponding interface card. So that way the control plane and the data plane of a router is basically separate. Now let us look into the control plane in a router. So as I was mentioning that a router is basically a special purpose computer. The control plane of a router is typically implemented as a software, which is ideally a router OS. So there are different kind of router OS like Cisco iOS that supports the basic computing functionalities to run a router along with the routing functionalities. That means the implementation of different routing protocol. So these routing protocols are implemented in the router OS. So whatever routing protocol you want to use, you can configure a router with the help of that routing protocol. And as I mentioned, the Cisco has one popular routing operating system, which is called Cisco iOS. Now, if you look into the routing functions are basically the route calculation. That means running, deciding that what is going to be an output interface. Then maintenance of the routing table, that to decide that in what periodicity the routing table will be updated. and the execution of the routing protocol, that whatever routing protocol you have configured, whether it is a distance vector routing protocol or a link state routing protocol, accordingly you can execute that routing protocol. Now on commercial routers, the routing functions are handled by a single general purpose processor. It is called a route processor that I was mentioning. Now if you look into the data plane of a router, now typically the data plane of a router, it implements the forwarding functionalities in the router. So it make the route lookup and forward the packet at a destination interface. The functionality is similar to a L2 switch. That means you will use a switch fabric. That means the mapping from the input port to the output port to forward the packet from one interface to the output interface. And it will maintain the interface buffer to implement the store and forward functionality. But the basic difference from a so the basic difference from a L2 switch is that this route lookup is a bit of complex, and that is why you require require special hardware to do that routing computation. Now, if you look into the IP forwarding mechanism, which is implemented at the data path of a router, so it is the per packet processing of the IP packet, and this IP forwarding is distributed, handled by individual interface controller. So for every interface controller, whenever it is receiving a packet, it will do a route match and then forward it to a corresponding outgoing controller, outgoing interface. And as I mentioned earlier, that we use a special hardware device for this purpose, which is called a TCAM, or ternary content addressable. Now, let us look into that how this per packet processing actually works. So you have a routing table. So this routing table is basically developed by the control plane functionalities, which is running at the control plane of the router. And then at every individual interface card, it has a copy of this routing table, and it has a routing decision engine which is running in the corresponding microcontroller or microprocessor which is there. Now, this microprocessor actually run or the forwarding functionality. That means whenever you are receiving a packet, you extract the header of that packet, find out what is the destination IP address, then make a lookup in the match of your local routing table which is there in your interface card. And if there is a match, you find out what is going to be the outgoing interface and forward that packet to the outgoing interface. Now, the mapping from one interface to other interface is through this switch fabric. So this switch fabric is more likely to a layer 2 switch. It will just forward the packet from the buffer of one interface card to the buffer of another interface card. So that is the task for this switch fabric. And once you are copying this, packet to a buffer of an interface card, then the scheduling engine will run to forward that packet to the outgoing channel. Now, the routing table which is there at every individual interface. So what I was mentioning, so this routing table. So the routing table, we have a global routing table which is being constructed by the routing protocol which is running at the router. Now, each network interface will keep a copy of that particular routing table. So this routing table will have a copy at every individual interfaces. So this copy may not be completely synced up with the original routing table that we'll see later on in details. So this local routing table, which is there in every interface card, we call that local routing table as the forwarding information base. So every interface, it maintains a forwarding information base or FIB. It is a mapping from input interface to the output interface. As I was mentioning, like a replica of the routing table is used at the interfaces for making the forwarding decision. And the forwarding works like this way. So you have a packet in, so you get a packet to the input interface. You make a lookup in the forwarding information base. If there is a FIB hit, that means you have a information at the forwarding information base. You forward that packet to the output interface and make a packet out event to forward the packet to the lower layer of the protocol stack. And if there is a FIB miss, in that case, you basically do a route lookup, look into the routing table. That routing table may in turn run the routing protocol to find it out, and then get that information to the forwarding information base, and then forward the packet to the output interface. So that means this forwarding information base, you can say it as a local cache of the routing table at the network interface, which is connected with every router. Now, the broad difference between the routing information base and the forwarding information base is as follows. The routing information base is actually your original routing table that was built up by the routing protocol. So it is implemented in software and is maintained at the control plane. And the forwarding information base is the copy of the required routes maintained in the interface TCAM hardware. So here is the main difference that I was mentioning. Like as I talked earlier, like this decision engine need to be very fast. So the FIB lookup that you are doing. So that is why you cannot keep the routing table in the software interface. So you need to make copy it to the hardware and then do a hardware processing so that you can process all the packets that you are receiving per second. And in a typical router, you can think of the rate at which you are getting the new packets. So that way, the forwarding information base is the copy of the required route, which is maintained in the interface TCAM hardware. Now, this routing information base is dynamic and it maintains the entire routing information. FIB is updated whenever it is required. So, the routing protocol which is running there, that routing protocol will actually build up the routing information base. And then the FIB will take a copy of it, put it in the hardware, and then do the processing. Here is an example. Say your routing information base, it contains the entire routing table. So this is the complete routing table which you have as your routing information base. Now this router say has two different interfaces, ETH0 and ETH1. Now one copy of that routing information base can be there in ETH0, another copy can be in ETH1. Now you see that this forwarding information base may not have the complete information which is there at the RIP, because you are copying them at the hardware, and the hardware has a limited space. That's why you do not copy the entire routing table. And sometimes for a large network, the routing table can be very large. So that's why you cannot copy the entire thing in your interface hardware. So you copy a part of it, whichever is required at that moment, that instance, and then do the processing. So if you have a miss here in the FIB, then you actually go for that route to look up in the routing information. Now, this RIB, they actually fits the FIB as I was mentioning. Now, RIB can be constructed from different technologies. So, the RIB can be constructed from the static routes that you are maintaining at your routers. They can be from the some inter-domain routing protocol like from the link state database. And they can also be from your BGP routing table. So the BGP routing table can actually feed the routing information base, and a copy of that can go to your forward table or the forwarding information base. So the routing table can be constructed any of the routing protocol or from the static routing configuration, and that goes to the forwarding table. Now, earlier we are talking about this TCAM hardware. Now, let's briefly discuss about how the TCAM looks like and how we can do a fast processing under TCAM hardware. So TCAM is basically one type of hardware memory structure which is called ternary content addressable memory. Before going to TCAM, let us talk a bit about what CAM is, content addressable memory. So CAM is something similar to RAM, your random access memory, but CAM does something called an exact match. So you have these different bits, and whatever input is given there, it can find out where there is an exact match of your bit stream in zeros and ones. And if there is an exact match, it can produce an output 1. If there is no match, it will produce an output 0. So that is basically the content addressable memory, where you can put up a table-like structure and then you can do the match. Now, this ternary content addressable memory is another advanced version of CAM. where rather than having two states, you have three different states. So from there, the name ternary comes from. So three states means 1, 0, and don't care. So remember that in routing table match, whenever we are talking about the about it in CIDR format, you have to actually do a prefix match. So prefix match means you have to do a partial match, and the remaining thing can remain as unmatched. So so that's why CAM is not very suitable for this kind of prefix match, because they are constructed only with two states, ones and zeros. Whereas TCAM, they have these three states, 1, 0, and don't care. So let us look into how it works. Now here I have an example of the prefix and the corresponding marks. So the prefix is 103/3, and in TCAM format, if I think about it as the 4-bit address, then you can think it as with a prefix 101 and mask as 3. In TCAM format, you can think it as 101x. So the x denotes the don't care condition. So this basically means that whenever you are getting a match at the first position as 1, the second position as 0, the third position as 1, the fourth position can be either 0 or 1. Similarly, for 111/3 in TCAM format, it can be 111x. For 10/2 in TCAM format, it can be 10xx. In 0/0, it can be all don't care xxx. Now here in the diagram, I show you the way this TCAM hardware looks like. So you have this every individual bits. Every bit contain one state, either it is 1 or it is 0 or it is don't care, and it is either 1 or 0 or don't care. So this 101x contains one row, 101x, then 111x, then 10xx, and then finally xxxx. And if there is a match, the corresponding line will be on. And finally, we have an encoder that will give you the final address of where you got it. So let us look into one example. So let us try to match 1010. Now, if I try to match 1010, my left-hand side bit LSB is 1. So let us take 1, try to match it. So in the first row, I have a match 1. In the second row, I have a match 1. In the third row, I have a match 1. The fourth row, it is a don't care. So I also have a match. My second bit is 0. So in the second column, the first bit is matched 0. There is a mismatch in the second column, that is 1. So whenever there is a mismatch, immediately that line will be off. So this particular address is not selected. Then in the third and the fourth, there is a match. So similarly, if we look into the next two bits, ones and zeros, they are also gets matched. So I have 4 different matches here and 1 mismatch. Now the question comes, when there are 4 different matches, which match you are going to select? So here, if you remember, we used to have this concept of longest prefix match in our CIDR notation. So here, whenever you are filling up the TCAM table with the help of your prefix information, we sort it in the form of that longest prefix match. So you see that this first row has the longest prefix where it got a match. Because in the first row, there was a match up to 3 states. If we exclude the don't care state, we have to exclude the don't care state. In the second, there was 2 states, there was exact match. And in the third, there were no state where there was an exact match. So we should take the first one. So because of this sorting mechanism, it will take the first address and that will go as out. So this is basically the broad philosophy based on which the TCAM works in the hardware to make and match with the routing table. Now, this is the part of the routing table which actually you are populating in the forwarding information base which you are populating in the TCAM hardware. That is my forwarding information base, a part of your routing table. Now here you can see that the number of entries that you can have in your forwarding information base, that is constant by the number of rows that you have in your TCAM hardware, right? So here it differs from your software-based routing information base. So in software, you can have any number of rows, whatever you want. But in hardware, you should have a fixed number of rows. So that's why we have these two different tables that are being managed. One is at the software level, my RIP. One is at the hardware level, my forwarding information base. Okay, so now from TCAM, if you remember that in the initial slides, I was talking about this concept of software-defined networking, and I was mentioned that this is the current network architecture where we are gradually moving. In many of the large data centers, people have already moved towards this software-defined networking or SDN-supported routers. So currently, our traditional routers, they are being replaced by these SDN-supported routers. So let us look very briefly about what SDN means and how SDN works. So this software-defined networking is a network framework which involves in separating a network's control function from its data forwarding function. So centralizing its intelligence and abstracting its underlying architecture from application and services. Now, if you remember that in our basic routing architecture, we have this data plane and the control plane. Now, the task of the data plane is to do the forwarding, whereas the task of the control plane is to build up the routing table. Now, the major complexity in a router comes from that complexity of the control plane, because the data plane is very straightforward. You have the information in your TCAM hardware. Whenever you are getting some input packet, you make a match and accordingly decide what is going to be the output interface and copy the packet to that output interface. So it is very much simplified. But the complexity is because your routing protocol is distributed, every router is running its own control plane, and the control plane of all the routers need to coordinate with each other to build up the routing table. There comes the complexity. And that is why we have seen that in case of distance vector routing, we have this count to infinity problem. In link state routing, we had the problem of having a large message overhead to get the entire information about your routing topology. And that's why we are constrained to some maximum number of hops. And that also brings up different kind of complexity to the network managers. So the network managers say whenever they are deploying a new router to an institute, they have to actually configure the router. So they have to decide that what is going to be the routing protocol. Then they have to decide like, even if they select that, well, I'm going to use OSPF as my routing protocol, then what is going to be my OSPF configuration? What is going to be my cost metric? So that way, there are 1,000 different configurations that you have to do whenever you are installing a new router. Now you see in an institute, these routers are deployed gradually. So some routers have already been deployed. Now I make a new network planning by separating out some subnets. So I have to deploy some new routers. And then the configuration of this new router should exactly match with the configuration of the old router. Otherwise, there would be inconsistency in the network, and there would be various problems starting from forwarding the packet to the security bridge. So that is why the life of the network administrators are actually very tough, because they have to do this large-scale management of a distributed system. From that concept, this concept of software-defined networking came, which basically says that in a router, you separate out the control plane from the data plane. So the router, which is distributed in nature, that will only have the data plane, but the control plane will be centralized. That will be pushed to somewhere in a central repository or a central processing unit, where it will generate the entire routing table and push it to the routers. So let us look how this particular architecture works. So that was the thing I was mentioning. So you have the control plane which takes all the decision. So the control plane works like an instructor. So it designs that, well, if you are getting this input packet, what you have to do with that packet. So it runs the routing algorithm. And the data plane is the module which carries out the task given by the control plane. So the control plane says that, well, if this is the IP address and this is the net mask and there is a match, then you forward it to IITKGP. So the data plane has to do this task. So do the match with the routing table and forward the packet. Now, traditionally, networking devices are proprietary. The vendor decides the software and the hardware. That means what is going to be the control plane, that is the software module, and the data plane of the hardware module. And there is actually no standardization. So typically, whenever you are purchasing a router from Cisco, you will get the Cisco iOS, which is the routing operating system, and they have their own configuration. If you are getting the network from Juniper, Juniper will have their own hardware and the software. Now in an institute, if you are interconnecting a Cisco router with a Juniper router, you have to do that configuration match, and you have to manually do all the configuration. So the life of a network administrator becomes extremely hard to do this kind of interoperability management. Now, let us see that what does separating control and data plane mean. So ideally, the vendors, they will only provide the hardware, that is the data plane, and we decide the control plane by writing custom logic, the software. So that means the software, I can make it centralized. The data plane will be distributed. That means I have multiple routers which will just do the forwarding task, but there would be a central unit which will decide about the routing table and push it to the individual routers. So the advantage is that the features are no longer limited to what the vendor provides, because the software is in your control. So you can build up your own API in the control plane. And nowadays, many open source software controller are available for doing this SDN kind of primitives, to support SDN primitives. You can actually write your own program on that open source control plane and deploy it over your network. So how does SDN work? So compared to a traditional network, a software-defined network has two types of devices, the controller and the switches. Now we call it switches because we are only constrained about the data plane. We do not have the control plane connected with the data plane. The switches in a SDN, we call them as the blind switch or the dumb switch. They do not have any inbuilt feature, and they need to be instructed by the controller. So whatever controller says, the switch just performs that task. So the SDN controller, it works like a brain of the network, and all policies, routing logic are placed in the controller, and it teaches the switch what to do with unknown packets. So here in this topology, say I have a SDN switch which is connected to different hosts, H1 and H2, and the controller is connected with that, and this controller will have entire routing logic or entire logic embedded with itself, depending on what the network programmer has actually done. Now let us see a scenario where a packet wants to go from H1 to H3 in a SDN environment. So you have a packet, and in that packet your source is H1 and the destination is H3. So H1 receives that packet. Now whenever H1 is receiving that packet, initially the H1 does not have any information where to forward the packet, because in its forwarding information base, it doesn't have that information. So there is a table miss. Now once there is a table miss, then it will actually make a packet in event, and that packet in event will send the signal to the controller. Now the controller is actually running the entire logic in a centralized way. The controller will find out that, well, how to forward that packet, in what outgoing interface the packet needs to be copied if they want to forward it to H3. And remember, the controller is a logical centralized entity. So it has the global knowledge about all the devices which are interconnected in that, or at least inside your server. So the controller will deploy that rule in the FIB of that particular switch, and the packet will be forwarded based on this particular rule. Now, next time when a new packet comes, you already have the rule installed in your forwarding information base. So you follow that rule and output the packet to the outgoing interface of S1 such that it can forward it to H3. Now, here is basically our SDN architecture. So I have the infrastructure layer. In the infrastructure layer, I have these programmable switches. So that is basically the data plane of the router, only the data plane of the router. The control plane is not there. So my route processor, all these things are not there. I just have the interface processor, the packet processor, along with the TCAM hardware, which is implementing the forwarding information base. And then I have a centralized network controller. That network controller runs the software that has the entire knowledge about the complete topology, based on which whatever functionality you want to implement here, you can implement it, and the controller will actually run it. And on top of the controller, now because it is a centralized logical entity, you can run your network program on top of that. And that network program can be various things, not only about routing. It can be a firewall, it can be a forwarding engine. Now, interestingly, here in this architecture, you can also implement a firewall in this particular way. Say, ultimately, your forwarding information base, what it dictates that if this is the IP address, if this is the destination IP and the destination subnet, then you forward it to this outgoing interface, say it is 2. Now, apart from doing that, if you set up a rule like this, If your network IP address is 10.2.2.2 and the corresponding protocol is TCP, then you drop that packet. Then that basically actually your firewall. Now, with the help of this architecture, you can implement a firewall engine on top of your network controller, and that firewall engine will accordingly set the TCAM rule, and that TCAM rule can be installed in the programmable switches. So here is the difference between your traditional network architecture and the conventional SDN architecture. Now, if you look into a traditional network architecture, every router will have its own data plane and the control plane. And the network applications which are running, they are running in a distributed way over different routers. Now, in case of SDN, what we are doing, we are separating out these control planes and having a logical centralized controller which is running the control plane. And on top of that, my network programs are, all my network programs are run. And the routers, they are the dumb switches with TCAM hardware, and they are just ensuring the forwarding behavior of the packets. So that way, my SDN architecture differs from the traditional network architecture, and gradually we are moving from this traditional network architecture towards the SDN architecture. And this is actually a very brief overview about SDN. So there are lots of internal things, and we can discuss it in advanced networking class. We do not have that much of scope here to discuss all those details. So if you are interested, so I would suggest you to look into different SDN protocol. There is something called OpenFlow. OpenFlow is basically the standard which actually says that how this controller will communicate with every individual data plane. So that communication protocol, setup protocol is called OpenFlow. It is an open source protocol. You can look into that. You can see that how the forwarding information base is actually configured in a OpenFlow based setup. And there are many, or there are numerous open source network controller which are available, SDN controller like Ryu, POX, and then you can search over the internet to see that, and then you can actually build it up on your own computer and try to do it. So there is an emulation engine called Mininet. You can actually program over Mininet to get a feeling about this SDN architecture. So if you are interested further, I would suggest you to explore it, or you can just drop me an email, or you can post it over our Piazza course link. I would be happy to share the resources with you over there. You can look into this open source forum. In this open source forum, that actually gives the details about this open source networking architecture. So this is all about the router architecture which is there. So this also completes our discussion about layer 3 protocols in a network. Later on, we'll look into some details like ARP, NAT, this kind of techniques, and then we'll move towards the layer 2. So if you have any questions from this particular content, feel free to post it over Piazza. So I hope that all of you are staying safe and taking care of you as well as your family. So in this trying time, we have to manage all the stuffs together, and we need to find out alternate solution about how we can go with our day-to-day life. So all the best to all of you. Stay safe. If you are facing any difficulty in any way, you can always drop me an email. I would be happy to discuss your problem with you. And also another information, like in Piazza, I'm posting some interesting links or interesting literature that we are getting. Even during this COVID crisis, we are getting interesting materials that you can try out. So it would be interesting to look into those kind of stuff. So I would suggest you to go through that and have our discussion over the Piazza forum. Thank you all for watching this video. Hopefully we'll soon come out of this crisis scenario. Let's hope for that. Thank you and bye-bye.